Okay. I think that we are live. Let me double check by looking at the transcript. We are? Cool. So, the last time that we met, we were looking at notes at 13. Our goal is to finish 13 today and get as far into 14 as we can. And if we don't finish 14, it's not the end of the world. We'll just start 15 our next class, and I probably won't even test you on anything too complicated from 14 if we do. 13 is where we left off, though, and I want to pick up there. And the idea was if we had a microphone, so we had our diaphragm for our microphone, and then we had a vent that allowed the atmospheric pressure. Can you not see my screen right now, guys? You can see my screen. Charbel can see my screen. Mikhail, you have to figure out why you can't see my screen. So we have this microphone. You might be just being dumb. Yes. So we have this microphone where we said that we had a pressure that was acting over the entirety of the microphone. For Love-Delman modeling, we'll assume that the length scale of the microphone is much. Yeah, Maddie brings up a good point. There's my face, and then there's the second Bread account, which is from my iPad. That's what you want to look at. Because the length scale of the microphone is much tinier compared to the wavelength of the pressure signal, we'll assume that the pressure is acting uniformly over the entirety of the microphone. And we discussed last time how the diaphragm of the microphone has its own mass, it has its own compliance, and it has its own damping. The cavity we discussed had what? We're going to neglect a lot of things, but the cavity had only what, if somebody wants to unmute and answer or type. That's correct. It only had a compliance. And the vent, we said, only had some resistance. If we assume that the diameter of the vent's very tiny and it won't be storing any kinetic energy, it'll just be strictly there as a dissipator. So that's how we will go ahead and represent the vent. And the circuit that we drew for LEM was to say we had this pressure signal that produces some volume velocity or has some volume velocity associated with it. And it was our job to figure out how things behave. So this volume velocity acts on the diaphragm and the vent simultaneously, which ended up leading to them being in parallel. So we said that there's a vent which has a resistance. This was our vent. And then the diaphragm, we'll say, is the mass, the damper, and the compliance of the diaphragm. That's mass of the diaphragm, R of the diaphragm, and the compliance of the diaphragm. And then they both meet inside of the cavity. We see that the diaphragm will deflect into the cavity, and then the vent will allow volume velocity to go into the cavity. So because that they are in parallel, they'll end up meeting again and both enter the cavity, which we're saying is just a compliance. And that was our acoustic model, circuit model of a microphone that looks like this, where it's simply just the diaphragm, a vent, and a cavity. Is that okay? This should be review. So we discussed a bunch of different sensitivities, basically relating domains in a sense. We had our overall sensitivity, which was our open circuit sensitivity, which was, volts per Pascal. That was kind of the overall circuit where we had some Pascal input pressure and some voltage output in the electrical domain. This was going through the entirety of our lumped element model, which we haven't drawn. This is just the acoustic model, but this is what we've been talking about a lot in class. The input leads to an output. I drew this block diagram last time. It's in the note set. That kind of goes through this chain of events. The thing that we cared about, though, for this type of acoustic model was the acoustic sensitivity, which we said was for a given volume, or for a given pressure, what is the volume change? Not volume velocity, but what is the volume change? And since our circuit doesn't have volume in it, at least currently, what we do is we find the volume velocity, and we were going to integrate that. And what we did last time is that we assumed it was harmonic. Everything was harmonic, meaning that we can express it like, we'll say that the volume is some initial volume e to the j omega t. That's what we mean when we say it's harmonic. It's sinusoidal in nature. And we would typically write this as some constant times the imaginary part of e to the j omega t, but I'm just dropping the imaginary. And the benefit of doing this is that if you were to take the derivative of this, with respect to time, that is the volumetric flow rate, the volume velocity. That just ends up dropping down a factor of j omega from the exponent. And you see that this v naught here with the e to the j omega t is just simply our volume. And what we discussed is that anytime you take an integral or a derivative, you end up bringing in this extra factor of j omega or 1 over j omega, just based on the fact that we're assuming that it's harmonic. Does that make sense, or any doubts about what I just said? Okay, cool. So what we care about is solving for volume. We see that volume just ends up being, if we divide by j omega, we get that, or maybe I'll just write it to be on the same side, q over j omega is equal to v, and that's what we use for our acoustic sensitivity. This is going to be q over j omega p is our acoustic sensitivity in general, but we have to be very specific, because in regards to the transducer, the thing that we care about is the deflection of the diaphragm. So really what we care about is not the overall Q, because the overall Q is split between the vent and the diaphragm. We only care about the Q through the diaphragm, which is why this Q ends up being Q of the diaphragm over the j omega p. Is that okay? Yeah, question. Misclicked. No question. Cool. So we ended up solving the circuit last class, or at least showing some of the steps of it using current division. We see here that we wanted to find what QD was. So we have this overall Q that's splitting between the diaphragm and the vent. So we ended up combining those impedances because they're in parallel in general to see what our total Q was, which we can find based on that combination, and then incorporating that with the cavity impedance. And then once we have that total Q, we can do current division to see how much of it goes towards the diaphragm. And that gave us some very long expression for the acoustic sensitivity. But the thing that we started to do was look at very specific cases of what would happen to the sensitivity at different regimes in our behavior. So what I started to plot last time, at least, or at least I gave you this plot and we started to show it, is that as a function of frequency, if we look at the magnitude of the acoustic sensitivity, what we saw is that because it's a microphone, there is no sensitivity at DC. So when omega is 0, because of the pressure equilibration, we don't have any sensitivity at DC. But eventually, as the frequency gets higher and higher, we do start to see a response in the microphone. And we see that that response ends up being approximately linear until we hit the bandwidth. And at that point, we are at the same sensitivity at that point. That's the whole purpose, though, is to be inside the bandwidth. So before the bandwidth, which would be anywhere to the left of here, we're not at a constant sensitivity as it's constantly changing as a function of frequency. But after, we see that we are at a constant sensitivity in this flatter region within plus or minus 3 decibels. But then eventually, as our frequency starts to get too high, we end up achieving what we would expect, which is some resonance, and that eventually it would die off. Make sure, something like that. Where the thing that we care about would probably be here. This is our bandwidth in this region. I don't want to do, it's not underneath the graph, but this is our bandwidth. And this region here, you know, is our damping and our resonant peak and stuff. This is our damping dependent region, which is resonance. And then we have our mass dependent region later on. What is going on? Why is there so much conversation happening? I have 2 accounts open. Can we see the screen? I need to make sure. I think everybody can see the screen. It's only like 2 people that are having issues. Charbel, I have a second account that isn't where my face is. There's another Brett Fracas, which is the iPad. Make sure you're viewing that in your gallery, and you'll see the screen. So what was the name of this frequency that we talked about last time? That's basically when our sensitivity becomes valid. What do we call that? That is the beginning of our bandwidth, but that specific frequency, that was called the cut-on frequency. This is the cut-on. That's the cut-on frequency. And that ends up depending on the vent and the compliances of our system. I don't know if we got that far yesterday or on Wednesday, but does anybody have in their notes how far we got? I know we did omega 0. I think we did omega is less than omega cut, and we saw that it was a linear response. Did we do the next part? Somebody can look in their notes for me. I don't remember where we left off. Omega is less than 1. I remember doing anything past linear. I see Tracy typing, so I'll let her type. But just to remind you while they're typing, there are 2 ways to really go about this. We have this long expression for sensitivity that we derived last time with current division, and we can plug in omega is 0 and see what happens. We can plug in omega equals omega n and see what happens. But another thing we can do is take the circuit that we drew and redraw it in such a way where we will neglect things depending on the frequency. That's helpful. Let's see. We have that SAC is equal to that. Perfect. Okay. So what we did last time, and I'll just kind of recap that, as we looked at three regions, we said omega is 0, and we saw that at omega is 0, the sensitivity, the acoustic sensitivity was 0. This is what we showed last time through our circuit. Because our circuit here, what ends up being the volume velocity through the diaphragm at 0 hertz? What happens to this leg of the circuit if we're at 0 frequency? Nobody wants to speak. Everybody wants to type.
Open circuit.
Thank you. Beautiful. That's so much easier.
Oh, open circuit.
Yeah, perfect. So the open circuit at 0 hertz, this opens, which means that we have no current flow. That opens. There's no current flow. So that means our sensitivity at 0 at that frequency. That was the big thing that we saw. The next example we did, we said that omega was less than the cut-on frequency. And basically what this means is that the capacitors are not open, but we will assume that omega is small enough to where we will neglect the inductors. Because remember, the impedance of a capacitor is 1 over j omega c, and the impedance of an inductor is j omega L or j omega M, if we're looking at masses, for example. If omega is 0, we saw that the inductor shorted and the capacitors opened. If omega is small, we will say that this is finite now, but we'll neglect this for simplicity. So if we were to do that, what we'll see is that our circuit, which has our vent, our cavity compliance, this is our C cav, so our vent, we will say that the inductor is shorted at this frequency, while the remainder of the frequencies or the components are not shorted or opened. And if we go through the math with that, we end up getting that our acoustic sensitivity ends up being j omega r vent, the compliance of the diaphragm, times the cavity, the compliance of the cavity, 1 plus j omega r vent C cav plus C diaphragm. And what we did was assume that if omega is very, very tiny, if omega is very small, not 0, but very small, we would say that 1 is much greater than that term. Which means that our acoustic sensitivity in that region is j omega, the vent resistance times the product of the compliances. Because if it's very small, this denominator just becomes 1, essentially. And this is linear with omega. Which is why in that graph I showed before, we had 0 sensitivity at 0 hertz, and then it increases linearly until it reaches the bandwidth. This is roughly the relationship for that leading up to the bandwidth, this somewhat linear relationship. Are there any doubts about that? Any concerns about that?
No.
Thank you. So,
No.
so the thing that we want to look at next is what is that cut-on frequency, so we know what the beginning of our bandwidth is. The cut-on is the point where the 1 is much greater than omega assumption fails. So what we'll do is basically say, let's say they're approximately equal to each other. We'll say that 1 is equal to that omega R vent, C of the cavity, let's see the diaphragm, and we can just solve for what omega is at that situation. This is omega cut at this cut on at this position. We'll say that that is approximately equal to 1 over R vent times the sum of the compliances. So if you had a model for your microphone and you had a representation of the vent, or you had a representation of your cavity and your diaphragm and stuff, you can determine approximately what your cut-on frequency would be for your bandwidth. In regard to your question, Mikhail, equal to or close to, because we're doing LEM, nothing is going to be perfectly equal to in general. And this whole idea of like, oh, let's just approximate this omega as being 1 over this R vent times the compliances added together. And just assuming that they're on this roughly the same order at this point, so that just gives us an approximation for what that cut-on frequency would be. Of course, when we go to fabricate and we do things like that, it will never perfectly match, but this is a pretty fair approximation to at least understanding the behavior of the sensor, where we see that the vent and the cavity compliance have a huge impact on what that cut-on is. Now, of course, the diaphragm does as well, but we see that our vent is the big factor here. That doesn't really relate to sensitivity. Our vent is kind of unrelated to the motion of the diaphragm, but we see in the frequency response, it ends up causing the cut-on to be at a certain position. In the real world, does cut-on have to be done with testing? In regards to like calibration, yeah, you would expose the microphone to different frequencies and see what the frequency response is. And you'll be able to see, okay, if we're at low frequencies, we're not going to have any sort of reasonable response. But eventually, you'll end up being in that region where it's flat, which is what we want to talk about next. Our next region is when omega is in between the cut-on and the natural frequency. Which we should expect this is the region of our bandwidth. And if we come back to the acoustic sensitivity that I had from the previous section, where we had J omega R vent, C diaphragm times C cavity, 1 plus J omega R vent, C cav plus C diaphragm. If we assume that we're way above the cut-on frequency, since we're above the cut-on, we'll now say that 1 is much less than that term, which allows us to neglect the 1. And if we neglect the 1 and we ignore this, we can see that a lot of things cancel. The J's cancel, the omegas cancel, and the vents cancel. We end up seeing that our acoustic sensitivity just depends on the compliances of the cavity and the diaphragm. And we discussed in the past how in the bandwidth is kind of our 1 over K, that's our stiffness dependent region. We see here that our sensitivity just depends on a bunch of stiffnesses. It depends on the stiffness of the diaphragm, because if it's really stiff, it's hard to bend. And it also depends on the stiffness of the cavity. If I have a cavity, let me draw 2 pictures and I'll see if you guys can kind of tell me the answer here. Let's say here's my diaphragm. I'll draw my diaphragm in blue. And they're the same exact diaphragm, but different cavities. Which one do you believe is going to be stiffer, harder to deflect? The left one or the right one? Or does it not matter?
The left one.
The left one. Why?
The left one.
Why? Why is it the left one?
Because as it squeezes, whatchamacallit, the pressure will increase a lot faster than the one on the right.
Yeah, I mean, it's harder to compress the left one. There's not really any space for the volume to go. It just, if you're assuming that both of them are at the same initial pressure, it is going to be harder to compress the left one. So we see that the cavity itself has its own stiffness associated with it, along with the general dimensions of the diaphragm. If you have this trampoline that is much smaller compared to much bigger, both of those things end up impacting the overall sensitivity of the device. Did I put the J in the other equations, or was it negligible before? Well, to answer your question, Maddie, we're really looking at the magnitudes. If I include the J or don't include the J, all that does is deal with phase. So if we just look at the magnitudes, we'll say that the 1 is much greater than or much less than the magnitude of that imaginary number. So in this situation, I probably shouldn't have written the J, but I just did that for the sake of saying that we're just going to neglect this relative to this term. Does this make sense, the acoustic sensitivity stuff? How we see that in the bandwidth, it really just depends on the compliances of the structure, which goes with what we talked about a while ago about this stiffness dependent region that is occurring in the flat region of our frequency response. Is that okay? Where's Lloyd? He's back there. Let's see. Our next region would be when omega is equal to the natural frequency, to get a feel for what happens in resonance. So without looking into the microphone for a second, I want to look back in time at our mechanical sensitivity from a spring mass damper system. So it's from the past. We looked at our typical spring mass damper system. Mx double dot plus Cx dot plus Kx is 0. And we derived what the sensitivity was, the mechanical sensitivity was relating, sorry, not 0, equal to force. What the mechanical sensitivity was, which is the ratio of the output displacement to the input force. So our mechanical sensitivity was X over F. And what we did last time when we looked at this is we took Laplace transforms, we solved for x of s over y sub s, plugged in j omega for s to see what the transfer function was as a function of frequency, then took the magnitude of it. And we ended up getting that the magnitude of this was 1 over the square root of negative m omega squared plus k squared plus omega c squared. This look familiar? It should look familiar, hopefully.
Yes.
Okay. So what happened at resonance? So at resonance, meaning that omega equals omega n, which is the square root of k over m. Let's go ahead and look to see what happens here. If we plug in,
Kid won't leave. Wouldn't let me talk.
no, you're unmuted.
Okay.
Research shopper.
Thank you. So if you were to plug in omega n in for omega, we get negative m times omega squared, which is just k over m, plus k squared, plus, I'll write this as omega squared c squared. It's going to be k over m times c squared. This term goes away. We see that? You have negative m times k over m. That gives you negative k plus k. That goes away. And we end up seeing that our mechanical sensitivity ends up just being 1 over omega n times c in that situation. Now, the reason that this is important is that if I were to draw a circuit of this system, oops, I hate that I use C. That's so stupid. Okay. Let's see. That's a damper. Sorry. What we see is that everything that has an imaginary component, you have j omega m, 1 over j omega times the compliance, 1 over k, all imaginary terms go away at resonance. They essentially cancel each other out. And this is true regardless of how complicated the system is, which is very convenient for us. If we assume that everything shorts at resonance, that makes our lives very, very easy. I know that's a little weird, like I'm just introducing this concept to you now, but what we see is that at omega n, this first term here was originally based on some j omega L, and the compliance is associated with 1 over j omega. Those types of things end up canceling each other out at resonance. And I wanted to use that old example to kind of demonstrate that for that case. But what ends up happening to our circuit, which I'll go ahead and I will just copy and paste from here. Is that at resonance, what we'll see is that our cavity will end up shorting. Our compliance ends up shorting. And our mass ends up shorting. And we know that in resonance, we're just dealing with damping in general. And this this circuit kind of shows that we really only have some sort of damping in this situation. And if we were to look at what the sensitivity is, we know that the sensitivity acoustically is 1 over j omega times q of the diaphragm over p. If you think about the fact that the effort drop across this resistor is P, we just have an Ohm's law type of thing. We know that P has to be Q diaphragm times R of the diaphragm. So that means that Q over P ends up being 1 over R. So our acoustic sensitivity is just 1 over J omega R of the diaphragm. This is at omega equals omega n. Does that make sense? Do we have any doubts about what I just said or did?
No. No.
Well, the R of the diaphragm is a very tiny number, Mikhail. When you're dealing with MEMS, a lot of these numbers are very small. So you have 1 over R of the diaphragm, which will end up causing the sensitivity to be larger. In regards, I'll just kind of summarize exactly what we just did, is that at the natural frequency, the thing to remember is that all of your imaginary terms will cancel each other out. And in that situation, what we'll do for our circuit model is just say that they all short because they all cancel each other out. And from that, we draw the circuit that we have here, where I'm curious on what the sensitivity is in this situation. So I need to find what the Q going through the diaphragm is, because this is the definition of acoustic sensitivity that we discussed at the beginning. So the Q through the diaphragm is going to be the flow that goes through that second resistor. Now, because these two things are in parallel perfectly, mostly because this cavity is now missing, we see that there's a pressure drop of P across the vent, and there's a pressure drop of P across the resistor for the diaphragm. They both are in parallel. They both have an effort drop of P. So if the effort drop or the voltage drop is P across the diaphragm resistor, we can say that V equals IR, that the pressure, which is like voltage, is equal to I, the diaphragm volume velocity, times the resistance of the diaphragm, V equals IR. And we can solve for Q diaphragm over P by bringing things over to one side. We end up getting this, which is what we ended up plugging in to there to tell us what our sensitivity is at resonance. That answer your question, Franco? I'm not sure if that was your thumbs up or not. I'll assume that that's your thumbs up. Any questions about that?
No.
Thanks.
Let's see.
No.
Put 'em up.
Oh, I just feel like Charbel and Connor together just saying no back and forth to each other. But I don't know. I can't be for sure. So let's say now that we're way past omega n, which we know should be something that's more related to the mass. So at high frequencies, what happens to the capacitors? Remember, 1 over j omega c.
They short.
They short. That's correct. All capacitors short. And if we assume that they're large, but they're not infinite, we'll say the inductors are still present, but ultimately they will open later on. So the capacitor is short. That's that compliant capacitor. We'll have our mass of the diaphragm. And we'll also assume that the mass of the diaphragm impedance is much larger than R of the diaphragm, the damping term, which is not frequency dependent, it's just a constant. But at high frequencies, we'll assume that that mass is really big, which basically means that everything else that we had on this side is going to short at those higher frequencies. So we end up with a very similar situation to the previous situation where you are looking for the Q through the diaphragm, which is just dependent on the mass now. But just like before, that's the Q with the R of the bend. Just like before, because they're perfectly in parallel, we'll say that the pressure drop has to be equal to Q of the diaphragm times the impedance of the mass, which would be J omega N of the diaphragm. Remember, this is still Ohm's law, V equals IZ. Except acoustically speaking. Now, for our acoustic sensitivity, which we said is 1 over j omega Q of the diaphragm times P, we see that this is going to be 1 over j omega times 1 over j omega M of the diaphragm. Do we see that? Basically, I divided both sides by P, and then I brought that over to the other side to give me what the ratio of Q to P is. And this tells us that our sensitivity is going to be 1 over, and if we're looking at magnitude, the negative sign doesn't matter. This ends up being 1 over omega squared times the mass of the diaphragm. And we see that at higher frequencies, we have a much greater dependence on omega. It's this omega squared term. If you've taken controls before and you've drawn Bode plots, we see that if you have something like a pole squared, you drop at negative 40 decibels per decade or something along those lines. Or you just have a single pole, it's negative 20 decibels per decade. This situation kind of mirrors that because they have omega squared, and that leads to a very rapid drop off in sensitivity because of the fact that the mass is so overwhelmingly heavy. And due to its inertia at such a high frequency, we cannot get it to move sufficiently enough to create a meaningful output for us in regards to an electrical output, let's say. Does that kind of make sense for people who took controls, at least? If you didn't take controls, I don't expect you to know the negative 40 decibels per decade type of thing, but is this okay? It's also hard to tell because I don't see anybody.
Not crazy, Brett.
Not crazy. Oh, that's good.
Well, one of them. The other one was a brick. No.
Cool. So, last one. Omega goes to infinity. In the last situation, if omega goes to infinity, all our inductors open. And all the capacitors short. all the capacitors short, which is what I'm showing in red here. But the inductor opens. So what is our sensitivity going to be? Remember, our sensitivity depends on the volume flow rate through the diaphragm.
Zero.
It has to be zero,
Zero.
because it's open.
Zero.
So
Zero.
oh my gosh. Our acoustic sensitivity has to be zero in the situation, because physically, because the mass doesn't have time to move and catch up with the frequency. If it's moving at an infinitely high frequency, the mass doesn't have time to deflect. From a modeling perspective, the impedance of the mass is j omega times m. So if omega is infinite, that means the impedance is infinite, and that blocks the current from flowing, the flow from going through that portion of the circuit. So at that very high frequency, that's what we end up seeing. So in the notes, I show a picture. Maybe I'll just go ahead and show it. Let's go ahead and just do this. Can you guys see this? You see the
Yes.
graph?
Yes.
Okay.
Yes.
So we see that we have this linear region which we derived that leads up to the cut-on. In the bandwidth, we have an approximation for what our sensitivity is. It depends on the stiffness of the device, the compliance of the device. At resonance, we have our sensitivity being dependent on strictly the damping. And then we see that at higher frequencies, it ends up dropping as a function of omega squared. And then eventually we'll go to zero as we go to infinitely high frequencies. Does that summarize things okay? I know this Teams meeting sucks. I don't like Teams meetings. It's hard to make sure people are listening and paying attention. If you are, I'm glad. Does this okay though? Or are there any doubts about this?
No doubts.
There are no doubts.
No doubts.
Love it. Who
Love
said
that.
that?
No doubts.
Perfect. So that's the end of note set 13. We are going to start note set 14. I'm going to try to do as much as I can in this note set in the next thumbs up saying team is terrible. Yeah, I know. So I'm going to start note set 14, which is meant to kind of tie all this together. At least everything we've seen so far. And the moral of the story is, like, when we look at MEMS, so this is note set 14. Which is, again, on circuits, our final circuits note set, circuits part 3. We have been looking at these lumped element modeling circuits just in one domain. You have some acoustic phenomena. We look to see how volume velocity is flowing, and we just did that with the microphone example. If you have a spring mass damper system, that could be in the mechanical domain. You have some force, you have some velocity. You could draw a circuit representing that. The question is, though, when we deal with MEMS, it's a transducer from one energy domain to another. So the question is, how do we actually model that as a circuit? And a very general picture that you might see sometimes, that you have some sort of transducer. Let's say that this is an electromechanical transducer. Where perhaps you have some input that is mechanical. You have a force and you have a velocity. That force and velocity are sensed or felt by the transducer, and in response, they will create some electrical output, which will have some current and some voltage. And that's just kind of the whole idea behind this class, the idea of we have something that we're going to design that will deflect, mechanically speaking, and then that deflection will be transduced into some electrical output. And the goal is, how do we represent this schematic as a circuit? How do we go from one domain to the other? And what I'm going to use to kind of illustrate this is we're going to look at capacitive devices. So I want to look at a very simple schematic of a capacitive device, which is just going to be based on a spring and a mass. And I guess before we jump into that, I want to remind you of the different equations that we've seen for a capacitor before. First off, we know that the impedance of a capacitor is 1 over j omega c. We've seen that a good amount. What was the relationship to capacitance and the geometry? Because remember, what we're doing is that if we have some sort of plates that are overlapping by some amount, what was our capacitance?
Epsilon A over G.
Yeah, epsilon A over G, where the G was the distance between the plates. The A is the area overlap of the plates, and epsilon was a property of the medium, air or something, that is in between the plates. Now, the final relationship that we have to keep in mind is that the capacitance is related to the voltage between the plates. So if I were to say, here's some voltage, what is the measurement of voltage between those plates? What is that related to? If I include a C and a V in an equation, what is the relationship, and what else do I relate it to, a third variable? Anybody remember? The big equation here is that the charge on the plates is equal to
What was the
capacitance.
question?
I gave you the answer, so too late.
Q equals CV.
Yeah, good job. So the capacitance multiplied by the voltage gives us the charge that is on the plates, essentially. And this honestly is used to derive this. They're related. But these are the three equations that I think are important for our next discussion. Definitely the last two. So let's go ahead and look at a problem with a spring and a mass. And the first thing I'm going to do is just say, imagine we have a mass attached to a spring. Be done. And I knew I drew this vertically. This is just commonly how it's done. We're going to ignore any sort of gravity or anything because I do not care about that for this problem. I'm just trying to prove a point. And let's say that this is essentially what a transducer looks like. If we have an accelerometer where we have a proof mass in the center and we have it attached to some beams, there's some mass and then there is some stiffness associated with those beams in general. Now, this is assuming that there's no electricity involved at all. Let's go ahead and say now that we take this mass in our picture and we bring it close to, or we bring a plate that is electrically charged closer to it. So now imagine the situation where I now have a plate that is fixed, and I say that this is charged in some way. And what we'll see is that perhaps the mass moves down a little bit. by some amount x naught. Because if you think about in regards to, let's say, two capacitive plates, there is a force that exists in between them. The charges are attracted to one another. There's going to be some force that exists between them. So if I were to put, let's say, negative charge on a plate nearby, any positive charge that's on the mass will accumulate close to the plate. And then their attraction will cause the spring to deflect some amount and the mass will move downwards a bit. And we'll say that this is our equilibrium position. Where now you have these plates that are separated by a distance of g naught. They overlap by an area a naught, and there's some permittivity between them that we'll assume is constant. We're also going to assume the area is constant. The g is what will ultimately change, but for our purposes, we'll just say that the initial gap is g naught, and the initial deflection of the mass is x naught. Does everybody understand the problem right now, or like what I'm doing at the moment?
Indubitably.
Perfect. So let's say we're in equilibrium.
Yes.
If I were to do a Newton's second law sum of forces thing, do sum of forces equals 0 for the static equilibrium, there is some electrical force that is trying to bring the mass closer together. And then, of course, we have the spring force that is pointing upwards to try to bring the mass back. And if we're at equilibrium, that means that these two forces have to be equal to one another. What is the mechanical force? What is it, guys? Somebody looking at this picture. Yeah, it's K times X naught, the initial
K times
deflection.
X.
Charbel, you're really good at answering questions like 10 seconds too late.
Sorry, there's a delay.
Oh, okay. So,
He's lying. I'm right next to him.
He's lying. He's right next to him.
oh my God. This mechanical force is the stiffness times the amount that the spring is deflected, which we just said, because of that attraction, it's deflected by X naught. And the electrical force is an equation that I'm not going to derive. We're just going to write out what it is. This electrical force ends up being the charge on the plates squared over 2 epsilon A naught. So Q naught is the initial charge, and A naught is the overlap area. This will become useful shortly. How'd you get F elect? It's a derivation we're just going to skip over. We're not going to worry about it. This is given. So that's when we're dealing with statically. You have this mechanical force and electrical force that counteract each other from a static perspective. And this is true if I have a capacitive sensor with beams and I have a bunch of capacitive plates that are overlapping. If I turn the sensor on, there might be some initial movement because of that electrostatic force, and the beams will bend a little bit. And depending on the length of the beams or their thickness or things along those lines that impact the mechanics of the beam, it'll deflect a certain amount. And it also depends on, how much charge is on the plates as well. So that's our static problem. Let's go ahead and look at this more dynamically speaking now. Let's assume that there is some external force that is acting on the system now. So I'm just redrawing this just to kind of show what's happening here. Again, this is charged. And what I'll do is say that there is some external force that's causing some acceleration. And I'm just going to say that if I sum the forces on the sum the forces, I'm just going to say that that is the net force. I'm not going to set it equal to MA like we usually do. I just want to find what the net force is in terms of our stiffness and in terms of our electrical force. So I'm going to say that this is equal to some net force that is acting on the mass. And this will be equal to Kx. You know, I'll draw my free body diagram just to kind of show this. Kx, not x naught. This is the overall x. You know, the deflection due to some external force. We still have this electric force where the charge is changing. So that's not Q naught anymore. That's some Q. I'll assume that this is the positive direction. Minus Q squared over 2 epsilon A naught. This is the net force that the mass feels. It's based on how much deflection it has made, which depends on the input force or whatever acceleration is provided to it. And it also depends on the electrical domain, how much charge is building up on the plates. Now, if we were, let's just keep this aside for a second. This is our net force that is acting on the plates. Again, we'll have some net force here. What does this look like from an electrical standpoint? The gap is changing, right? Because if the mass is moving closer to or further up due to some external thing, our capacitance is now a function of some displacement. And you know what I'll do? I'll say that. So originally, this is at some position x naught. And I'll say that any deviations about x naught, I'm going to call a tiny deflection like x prime or something. Like a little tiny fluctuation about the equilibrium point x naught. So I'll say that the capacitance as a function of x prime, this will be epsilon A naught over the gap, which is now a function of x prime. And remember that initial gap was G naught. I'll scroll back up so we can look. That initial gap is G naught. If the mass has moved closer to the plate by some amount x naught, what would I write in my denominator? Remember, they've gotten closer. So it's originally G naught, and now it's gotten closer by some little amount x prime. What would I write in the denominator? Sure, but I want to include G naught.
G naught minus X prime.
That's correct.
G
Yeah,
naught minus X prime.
I knew that they were together, and I knew that they were copying each other. That's proof. So.
No, I'm not. I'm at the library.
No, I'm not. I'm at the library. This is our capacitance as a function of that deflection. The capacitance is going to change, right? If the gaps get closer together, the capacitance has to change. So what I'm going to do is I'm going to manipulate this a little bit. And I'm going to factor out that x prime from, x prime, no, I'm going to factor out G naught. Sorry, I'm going to factor out G naught. 1 minus x prime over G naught. What is this?
Capacitance?
It is capacitance, but what specific capacitance? It's the OG capacitance. That's right.
Oh, the
original
OG.
capacitance. That's the original capacitance, right? So this will be C naught over 1 minus X prime over G naught. This is our capacitance of the function of X prime. So if X prime is 0, well, it hasn't deflected. Our capacitance is just C naught. If X prime becomes some non-zero value, then it'll increase or decrease depending on if it moves closer to the plate or further away. Is that okay? Any concerns about this right now? So that is our capacitance. We know that Q equals VC, which means that V is equal to Q over C. You'll see why it's useful to, I mean, the reason it's useful to do this is because it's always nice to have things in terms of the initial capacitance in general, but we're going to write this equation slightly differently in a second. So the voltage, which will depend on the capacitance, will be Q over this term. So we'll do Q divided by C naught divided by the 1 minus X prime over G naught. That will just end up being a multiplication at the top. And we'll say that this is our voltage. So we have two equations now. We have one for the force, the net force acting on the sensor, and we have one that is representing the voltage that is acting on the sensor. Let me go ahead and write those down. We have two equations. Our net force was Kx minus Q squared over 2 epsilon A naught. And our voltage was Q over C naught, 1 minus X prime over G naught. Do you see from like a Lump-Dellman perspective, we have efforts, some force and some voltage related to flows, some, well, not flows, displacements, some X and some Q. They're almost flows. Remember, they have to be in the form of velocity. But we see that we have this general idea here, where we're relating efforts and flows. Now, what we would like to do is write this in a way that's linear. Do you see currently that this is a nonlinear? These are nonlinear equations. This is nonlinear. Because of Q squared. And this one's nonlinear. Why is this one nonlinear? My dependent, or the variables that I care about are the Q and the X's. So in that second equation, I'm multiplying Q by X prime, and that ends up introducing a non-linearity. Is that okay?
Yes.
And we typically don't like nonlinearities, right? Nonlinearities we usually avoid. We want things to be linear. So what we would have to do is linearize. We need to linearize the equations. which will involve saying that our Q is some initial Q plus deviations and our X is some initial X plus deviations, and we'll go ahead and do some math to get rid of any small quantities ultimately. And I have this all in the notes. I don't think I'm going to test you on anything from note set 14 because the hurricane screwed us up and we only have 2 minutes left and I have a lot more to do. But I have to start fab on Wednesday. So what I think I'm going to do, don't laugh. What I'm going to do is I will leave this, I put this note set on Canvas because I know that there are students in the class who wanted to understand this. This note set will be on Canvas for you. What I might do is have extra credit on the test that is based off of this note set when we get there. Charbel, put that face away. So the moral, though, ultimately, I'll say after lots of math, I just want to sum this up. We will end up with an equation that is relating our efforts and our flows and I go through the proof and the note sets about what this looks like. And this is a matrix representation of our transduction. Okay, that's freaking weird, man. There's a matrix representation of our transduction. And what we learn, if you go further in the note set, is that this matrix representation can be accomplished using a transformer, where we'll use a transformer to go from one domain to another. And I guess to just like provide one final thing, because I know that timing is not on our side this semester, and I'm sorry, it's so annoying. But if we had an accelerometer, an accelerometer is taking in some force, there's some velocity associated with it, and it's like a spring mass damper system. It moves, everything's in series, just like a normal spring mass damper system. What we would do ultimately, and I showed this in the notes, is that if you were to put a transformer across this, with a very specific turns ratio, you can go from the mechanical domain to the electrical domain. And by doing that transformation, you can relate force to voltage, which ultimately gives us that open circuit sensitivity. And we can predict and estimate what that open circuit sensitivity is, which can help us better design the sensors. I did not go into as much detail with this. I do not have time to, which is why this will be an extra credit thing. Don't stress about this if you do not understand, but if you're interested, I encourage you to read it. I know there's at least 2 students in the class that are interested in this stuff, like a lot. This is here for your disposal. Take a look at it and come ask me questions if you have any. In the meantime, that's all I have for you today. We'll start fab on Wednesday and we'll go from there. And that should be a little bit different compared to what we've been doing with the math and stuff. If you have questions, please come talk to me. I hope you're okay with that. If you're not, also come talk to me.
Do you have like $20 for gas I could have?
So come talk to me if you have any questions and we can go from there. Are there any questions right now from anybody?
What project?
No.
No.
Let's go say hi. Who's that? Oh, they're going.
She was like,
Oh my
"Who's
God,
that
cute
person
doggy.
talking?"
That's a cute dog.
Lloyd, over there.
Hello, Lloyd.
You good boy. This is my baby. He is very cute, even though he's a little sick right now. We're both sick. Leave. All right. I'll try to bring him to campus sometimes. Yeah, he has tummy issues like me now. Exactly. He's always had tummy issues like me. I'm gonna stop the recording. He